All right, here we are for another AP biology video. This one, as you can see, is about something called adaptive radiation. But the theme here is applying speciation over time and seeing how species have evolved and how this works in accordance with time. So this is one of the main slides from the last video, that there was two different versions of speciation that we talked about, where in one version, one species slowly turns into the next, and in another version, they split off or diverge. And that's an important word there, right? So this is divergent speciation. And I suppose you would call this linear speciation, right? But there's a word here that I used last time, gradualism, that applies. And so gradualism, where one slowly changes into something totally different, like so. But here's another definition for gradualism: when an evolution occurs slowly over hundreds or thousands or millions of years, a long time, right? And so this is one version of gradualism that I showed you. However, there's gradualism only has to do with speed. And so technically this one is also gradualism. As you can see, it's labeled gradualism. Now, this one is divergent in that the original group split into two groups. But the thing is that once the groups split, you can see that there's this slow from like yellowish to sort of white color going on here. And then this one's from the dark kind of orangish to more and more and more orange, right? So both of these are gradualism because there's slow changes that are accumulating over a long period of time. But that's not always how it happens. In the fossil record, there are some places where there's these big jumps or leaps in evolution, and we call that punctuated equilibrium, where evolution occurs rapidly after a long period of stasis, right? So, for example, here's one long period of stasis, right? The orange butterfly has stayed the same for a very long time after quickly speciating and diversifying by evolving very quickly right there, right? And then again, here you have another split where very quickly they split, but then after they split, they stay the same for a long time, right? And so there's a lot of different combinations of how this could work, right? There's no one way that evolution happens. It can happen quickly, it can happen slowly, it can happen divergent, it can be linear, right? And it could be any combination of those as they go along, where for a while there, it'll be gradualism, and then suddenly there might be punctuated equilibrium, and then there'll be a long period of stasis, and then maybe it'll go back to punctuated equilibrium, right? There is no like it has to happen this way idea, right? Now, the thing is that we're going to start getting into these diagrams more and more, but these diagrams, they kind of show time, but they also don't really show time. So I like this this graphic that shows gradualism versus punctuated equilibrium as well, right? Where this time they're getting away from pictures, right? It's purely just how much evolution happens over how much time, right? And so in the gradualism one, right, it's just one long straight line, just slowly going. Whereas in punctuated equilibrium, it evolves quickly, then it stays the same for a while, and then evolves pretty quickly, and then it stays the same for a while and evolves pretty quickly, and so forth, right? And so those are two models that you might have to identify, gradualism versus punctuated equilibrium. And so that idea brings us to this idea of time, like I talked about at the very beginning, right? How quickly does this stuff happen? And it all depends on the environment, really. The stability of the environment in particular, right? Of course, biotic and abiotic factors are really what drive natural selection, or the availability or unavailability of biotic or abiotic factors is really what's going to decide which variations are helpful at the moment, right? But if the environment is staying very similar, it's staying stable, then probably you're not going to get much evolution, right? You think about the horse example, where the horse ancestor was very small and lived in their nice environment, but the environment slowly changed from a foresty environment to a plains kind of environment. So the horse slowly changed from a small little deer looking thing into the big horse looking thing, right? If you think about it, like the animals that live in the environment, they have adapted to those environments. And if the environment doesn't change, then their adaptations are still viable. And so, of course, if nothing changes, then why would the animal change? But then the flip side of that would be that if the environment starts to change quicker, more quickly, faster, then evolution would happen faster, right? Because as every time the environment changes, there would be new variations that would be beneficial that maybe weren't beneficial in the last generation, but the environment has changed since that first generation was born, and so now a new trait is beneficial. But also, if it's still changing and there's a lot of fluctuation in the environment, maybe in a few generations down the line, then that what was the new beneficial trait, maybe that one becomes unhelpful and a new trait becomes beneficial. Or to really get it crazy, what if the original trait becomes beneficial again, right? So in the beginning, you have a trait that was beneficial, the environment starts changing, suddenly there's a new trait that's better, but then the environment continues changing, and maybe that original trait is now the better one again. And so this is an interesting thing where people would say, like, sometimes an organism would evolve backwards, but there's no backwards, there's only forwards. You can only have babies that have the traits that are hopefully beneficial, right? And if you would think of it this way, it would be more like a U-turn rather than going backwards. I know that when you do a U-turn, you go head back the same direction you came, but you weren't moving backwards, right? And so the environment that is changing is what's driving the speed and direction of evolution. Of course, if the environment changes too quickly, then this could lead to extinction because you have to have beneficial mutations that already exist for natural selection to work. And if the environment changes so fast that there aren't any mutations and there isn't any time for a mutation to randomly show up, then the species might just die, right? And so keep that in mind, that we have our basic natural selection and speciation, and then there's all these different versions of how it could happen depending on the rate and direction of evolution. Now, one of these special examples is something called adaptive radiation, where many species evolve from one common ancestor. And we're going to see that this is something that happens in a very particular type of environmental situation. The most famous example are Darwin's finches, which I know a lot of you are like, oh, finches again. But finches are a simple example, and we have a lot of data. And so this is what we'll go through it really quickly. As you know, there was an original common ancestor from the South American mainland, from Ecuador over here, right? And these finches that look like this, they still exist over here in Ecuador. But the Galapagos Islands are way over here, and they're far enough away that animals don't just go there just because. Birds aren't just gonna fly out there for a day trip. But they're not ridiculously far away so that no animals could possibly ever make it there. But they are pretty remote islands. And so basically somehow, probably a big storm or something, blew a population of the mainland finches onto the Galapagos Island. And here is where they encountered this very interesting environmental situation, which is that these are, in effect, desert islands. Not that many organisms have ever made it out here. When the birds arrive, they find some penguins, and some tortoises, like we talked about before, and some iguanas, some very special, very unique marine iguanas, but very few other birds. And so when they get here, they're able to just spread out everywhere they go, because wherever they go, there are no competitors. And this is the key, is that the selection pressure has kind of gone away in a sense, and that while they still need to eat and they still need to find food in an environment that they've never been before, and they're probably trying to eat things that they've never eaten before, they don't have that immediate pressure of, oh man, I got to do this quickly because if I don't, something else is going to eat it. Or I better move quickly because if I don't move quickly, something's going to eat me. Those things are not present on the Galapagos Islands. So the birds kind of have an opportunity to evolve without too many consequences, I guess, right? Now, each of the islands is a little bit different from each other, and so the foods that they find on the different islands are different. And you know the story that on the islands that have the big seeds, only the birds with the biggest beaks were able to survive, so the birds on those islands have bigger beaks. And then on maybe this other island, there's a lot of insects, and so you need a kind of a sharp, pointy beak to get insects. And so again, this is still natural selection. The ones that had the sharpest, pointiest beaks were able to eat the insects the best. But again, the thing is that even if you're not particularly good at doing this, you can kind of fumble around out there and find some food and find a way to eat it, right? Where again, in other places, there's intense competition. And so the birds probably wouldn't have that luxury to just kind of survive. They have to survive or they don't, right? But they have this new situation, right? So the birds spread out to all the different islands and they find all these different opportunities. Those opportunities are called niches or a niche. A niche is the way of life, the role in an ecosystem, right? And so I like this table because it kind of just lays it out nice and neat, right? A niche is like a job title, a climber, a glider, an insectivore. These are ways that organisms can live, right? Like if you are a small mammal or a small predator, maybe you're going to be really sneaky and you're going to ambush your prey, right? That is a viable strategy. And since it's a viable strategy, it is any organism, if that role isn't filled, some organism is going to fill that because that's a possible survival strategy, right? Chasing them down, that's a possible survival strategy. So in this table, they're showing Australian marsupials on this side, right? Because marsupials are like kind of an offshoot of mammals. And the important thing here is that they are isolated to Australia. So there wasn't a lot of, there's reproductive isolation there, right? And so on Australia, you find all these organisms that look just like the mammals from other places in the world, but that's because they have the same niche, right? And in Australia, you can still be a stalking predator. You can still be a chasing predator. If you're in North America, you can also be a stalking predator or a chasing predator. However, if there's already a stalking predator there when you show up, then you're probably not going to get to be a stalking predator, right? Because that niche is already filled. So again, this goes back to I'm going to go here first to the birds, that the niches that they found weren't filled. So they were able to diversify very quickly and spread out, right? And they've spread out to fill all kinds of different niches, right? Some of them eat seeds, some of them eat flowers. Some of them eat just the flower buds. Some of them eat insects. Some of them do this in the tree, whereas some of them do it on the ground, right? The niche isn't just like, oh, I'm in this spot. It's, well, I'm in this spot, but I'm going to stay down here. And they don't really talk to each other, but they kind of decide, oh, well, I'm not going to compete. I don't want to go, if there's already birds down on the ground finches are already starting to develop. Well, if I'm showing up, I'm not going to go on the ground. I'm going to go somewhere where there's nothing else to compete with, right? And that's where, come back to here, the video you watched of the lizards from the Gulf of Mexico, right? They have really, really diversified in terms of their micro habitats, their micro niches, right? There are 7 species that all share what's basically the same habitat, but this one only lives on the ground. This one only lives on the small branches. This one only lives on the medium part of medium trees. This one lives at the top of medium trees. This one lives at the top of the very tall trees. This one only lives on the fence posts. This one lives on the fence boards, right? Like there's so many different micro habitats that they have all adapted to. And if you remember, this is because of hurricanes, right? That hurricanes will come through and wipe out entire islands worth of lizards. And so when they show up on these islands, then there's all these habitats that are open. They get blown to a new island and they get to exploit those habitats. Now, the animal video was a great example of speciation because it had parts of just about everything. It had geographic isolation where the lizards were, well, in this case, in the video, they literally moved them to another island, right? Like the scientists did this on purpose, but it happens naturally as well. That is, a group will get isolated and then natural selection will start to happen. They will adapt to their new environment, and maybe part of that adaptation is to get a different colored dewlap, right? And the dewlap is important because that's how they reproduce. And so when the dewlap changes, basically makes it so that this lizard doesn't appear like the same species to the other group of lizards, right? The females are going to look at this one and say, hey, I'm looking for ones with the dark red. I don't see one with dark red. I see one with orange. You must not be a viable mate for me. So they don't even try to mate, even though they probably could, especially at the beginning after they haven't been separated for too long, right? But this is a great example of geographic isolation, where natural selection will then work to change the traits. And then when the two groups meet again, one trait in particular, a mating trait, changes them, and now they're separated by behavioral isolation, right? And this has happened over and over. One of the really important things about the video was showing that these diagrams show that on every island you have basically the same kinds of lizards, the canopy ones, the grass bush ones, the twig ones, but they're not actually that closely related to each other. That on an island, there was an original ancestor that then did an adaptive radiation to all the different other lizards. There was a different ancestor for this island. There's a different ancestor for that island and that island, right? Like adaptive radiation is happening over and over and over in these in the animal species, and so that's why it's a really great example of adaptive radiation, right? Now, adaptive radiation doesn't happen that much because usually if you're a bird that gets blown into some new island or some other area, there's already going to be competition there. And then you probably just won't even make it. Of course, this gets into things like invasive species that we've talked about. We haven't talked about before, but you learned in freshman year, and we will eventually talk about again. And so sometimes a species will show up and just take over, but that's not exactly what we're talking about. Adaptive radiation happens usually when you find a lot of open niches, which means this brings us to another part of how speciation over time, mass extinctions, right? There have been 5 mass extinctions according to the fossil record. And we are currently probably living through the 6th mass extinction. These extinctions have all happened for a lot of various reasons. We don't exactly know why all of them have happened. Every single one of them has competing hypotheses. A lot of them have to do with actually climate change. For example, this one right here, and so in case it wasn't clear, the bar width, how wide this is, shows how many different species there are. So right here, there's fewer species than there were right here, right? And that's where speciation has been happening, that more and more niches are becoming occupied. But then you have these places where the bar gets real skinny all of a sudden, right? Mass extinctions. And so this one, like I was saying, this is one of the most famous ones. It is the biggest mass extinction that's ever happened. It's sometimes called the Great Dying. Something like 70% of all land animals and 90-something% of all marine animals went extinct during this time period. And again, there's a lot of different theories. The leading one is that that Pangea was forming at this time, right? The continents are moving around. And when they do that, the ocean currents start to shift. And so when Pangea formed, it definitely screwed up all these ocean currents that used to go in between the continents. And this led to huge, massive climate change because the ocean currents help to regulate the climate. By the way, this is actually a thing that is currently worried about here. We know that ocean currents regulate the temperature on Earth. And as the ice is melting and of course global warming is happening, this is starting, it looks like, possibly changing ocean currents, which might lead to huge, even worse climate change, which of course this is not going to be a good thing. But there is a sort of a good thing about mass extinctions. Every time there's a mass extinction and the lines get skinnier, they immediately go right back out because speciation happens, right? After the mass extinction event, there's all these open niches that were previously occupied, and now you can go and spread out and adapt to all these new environments, right? Now, the Great Dying has the steepest, what do you call it, extinction rate, right? Like the bar gets real skinny really quickly, but it also has the quickest recovery. Look at how steep, just exploding back out, right? Because the more you kill everything, as long as there's at least some survivors, those survivors are going to have a huge advantage that they never had before, which is they can basically go wherever they want to go, right? Now, the most famous of these is at 65 million years, right? That's when the dinosaurs went extinct. And on this one, there's a lot of evidence to show that it was from an asteroid, meteor, whatever it's called, when a giant rock from space hits the Earth. Um, Although there are other things like volcanic activity that's going on and climate change again. But the important thing is that with the extinction of the dinosaurs, this opened up a ton of niches for our ancestors, the mammals. In this image, you can see once again the width of the line shows the number of different species, right? And so first off, you notice that the mammal line goes way back. There were mammals alive at the same time as dinosaurs, just like crocodiles, which, by the way, are not dinosaurs technically. And then the ancestors of the birds showed up alongside dinosaurs for a while. And then the dinosaurs stop, right? And as soon as the dinosaurs go away, the mammal line explodes out. The birds a little bit, but the mammal line for sure, because the mammals and the dinosaurs were direct competitors, right? If you were a small, and of course, the ancestors at this time, the mammal ancestors at this time, were very small rodent-like species. And so when they poke their little heads out of their holes, because usually we think that they probably lived underground, because if they come out onto the surface, there's tons of dinosaurs everywhere. You poke your head out, you see some seeds over there. Oh, I would like to eat those seeds, but there's a dinosaur eating those seeds. Oh, that's okay. I'll try to eat those leaves over there. Nope, there's a dinosaur over there eating the leaves. Then, of course, you try to go over there to eat those said leaves, and some giant dinosaur just eats you, right? So life is tough for the mammals. They're small, scavenger type organisms. But as soon as the dinosaurs go away, they have free reign, right? To roam wherever they want to go. When you poke your head out of your little hole and you see some seeds and you say, oh, I would like to eat those seeds, go for it. There's no dinosaurs over there to eat them. They're gone already. The leaves that were over there that used to be eaten by dinosaurs, also available. Now, of course, if one group of primitive ancient mammals comes out and starts eating seeds, and another group of mammals comes out and they're like, oh, I want to eat something too, they're not going to go to the seeds. They're going to go to the leaves, right? And so as this happens, just like with the anole lizards and with the Darwin's finches, they're all going to spread out to wherever they can find. And then this would lead to all these mammal species showing up that didn't exist before, right? The adaptive radiation of mammals could only have happened thanks to the mass extinction of the dinosaurs. I like this example a lot. This animal on the screen is something called a civet. It is, in my estimation, my personal opinion, a weird looking animal. But I like it because it looks like a lot of other animals, doesn't it? Right? It kind of looks like a raccoon. It kind of looks like a cat, kind of looks like a dog. It kind of looks like a hyena, right? If you know what a hyena looks like. It has spots that are kind of like a leopard, right? Like there's all these different traits in this one animal. And it turns out that the civet is the modern descendants of what would have been the first carnivore. The first carnivore probably looked like this, right? Kind of similar to what it looks like now. So the civet, again, is not the ancestor. This is the modern version. This evolved into that. So you can see there are some changes, of course. They're not exactly the same. But something that looks like a civet is way back here, right? And then this was the first carnivorous mammal, basically. And it started to spread out all over the world, right? Like there is an opportunity for carnivores everywhere. And so it's split into basically three kind of groups. One group came over here, and then that led to cats, felines. And then over here, there's another split that leads to the civets. That's what this one is. And then the hyenas. Look, the hyenas are their own group. Hyenas are closer to cats than they are to dogs, although they aren't either. They are this weird kind of like giant civet thing, right? And again, you have this split here from speciation happening. Up here, you have, what do you call those? Weasels. Weasels. And then these are seals that don't have ears. So I believe those are traditional seals. On the other side here is the branch into the big dog-like carnivores. You have dogs themselves right there. The bears broke off really early, and then this one right here is a raccoon, and then these are sea lions, seals with ears, water dogs, basically, right? But they all have their ancestors going back to this ancient civet-looking thing, right? Because this one has all these different traits that could be amplified in one species and then not amplified in the other group. And so they start to diversify thanks to adaptive radiation. This is what the original mammal probably looked like. Little scurrying rodent looking thing, right? And if you really could stretch your mind onto it, like these things aren't that different, right? Like, there's a lot of differences, but they're not that different in that you couldn't have a lot of natural selection to lead from one to the next over a lot of time, of course. So that's just the carnivore arm of the mammal radiation. This is the big evolutionary tree of the mammals. Way back here is the most ancient and primitive of all the mammal-like things. These are monotremes. These are platypuses. These guys still lay eggs, right? But they also have fur. They make milk. The platypus, though, is super primitive. They don't have teats. They have mammary glands, but the glands are basically just embedded in their skin. So platypi, they basically sweat milk, and then their babies just suck the milk off of the like wet fur that like they sweated out, and which is weird. But again, like this is the beginning. Then there was a split to go to the marsupials. Marsupials don't lay eggs, but they also, their babies are born super, super early, like when they're just tiny little like pink embryo things. The embryo little fetuses crawl into the pouches and then they finish developing. Over here, though, is the main group, with is the placental mammals, meaning that we actually like the babies stay inside for the entire time until they're ready to be born, and then they come out, right? And that's the mammal thing to do. There was a big split early. This split I find kind of interesting, that this one leads over to elephants, right? Elephants are a significantly different branch of mammals than these rest of them, although they are more similar to anteaters, right? Is an elephant kind of like a giant anteater? Sort of, right? Again, there's a lot of other traits that changed, but they do have that long nose thing going for them that almost all other species don't. The other species that do have that long kind of nose are these guys, though, like elephant shrews, I think is what they're called. So that's one branch of the mammal family. Then on the other branch, you then have two significant groups. The one on the right here goes into what we usually think of as like the main set of animals. Here's the carnivores, right? So here's a lot of the predators. But then there's two groups of sort of prey, and they go by their, they're actually grouped by their feet. This one right here, it says dactyla. That means toes, basically. These guys over here are the, oh, I always get this wrong, the even-toed. They're called even-toed ungulates, which means that they eat grass and they have multiple stomachs and stuff like that. So camels, deers, giraffes, what do you call that? Cows. These are all in the even-toed ungulates. And then over here is a branch, and here you see the dactyla again. These are the odd-toed ungulates. So these guys have hooves, just like these guys do, but these guys' hooves are made out of their middle two fingers, toes. And then the horses and the rhinos, they only go on their middle toe only. And so they're the even or the odd-toed ungulates. There's a couple other random ones here. I always find it weird that the bats kind of just shoot off over here. Like that's not really what I would have expected. I would have expected the bats to be more over on this side with the rodents, right? And this is basically, and notice the primates are over here with the rodent group. Again, a monkey is kind of just like a squirrel with really long, skinny arms and legs, right? And then a different kind of tail. So you have your rodents over here, you have your primates over here, and then the rabbits are all by themselves, right? Where does a rabbit fit in? They don't really fit into anything. They're kind of like big rodents. They're kind of not, they're not really like primates at all, though. And so these are all the mammals that all evolved thanks to the disappearance of the dinosaurs, right? And then, of course, we're going to talk about this more, but here is the biggest tree of life, right? So that what we were just looking at, that was just this right there, right? And so then there's a whole nother one of those for all these other groups. The mammals came from reptiles, which so did birds came from reptiles. So if you follow the bird one back, it goes to the reptile, to the green. Of course, the mammal one goes back to the green. The reptiles are the green one. The green one goes back to the blue, which is the fish, although the amphibians are kind of in there too, right? Like the amphibians came out, and then there's the fish. And then before fish, it gets really crazy. You have a lot of insects and marine animals over here. And then these things are not even considered animals, of course. These are plants and fungi and bacteria and things. We'll get to all this. It's way too much to look at all at once. In fact, just to make this diagram, they had to like rotate it and like bend the tree. And of course, there's tons of things missing from this kind of thing, right? But this is all thanks to speciation over time. Natural selection plus speciation with some mass extinctions thrown in there, adaptive radiations, and thanks to all those things, we have the current life that we have on Earth, right? And so here's where we're now going to start looking more and more at the way that organisms have evolved from each other and how they're related to each other.